Hey all.
Hello.
Hey Dave.
Hey. Got some weird shadows. Hold on a minute.
Hello. I'm having some trouble with my camera, so I'm gonna restart my Zoom. And hopefully that fixes it.
Well, that's better. We just lost Catherine. All right.
She's restarting her Zoom.
Okay. Well, I might have to do the same. Oh no, I'm good. All right. Well, we're just waiting for Catherine, then we'll get started. Jack, I got an email from you. Oh, it's on Piazza. Do we have class today? Yes, Jack, we have class today. Morgan, you're slightly swaying back and forth, but you're stationary, so it just looks like your background is swaying back and forth. It's a little bit disturbing.
Try not to. But I'm in a hammock chair, so.
That's all right. You gotta stay comfortable. It's all good. So our plan for today, I don't know where Catherine went to, but our plan for today was just not to cover any new material, but just to give you more hints and explanation of the homework, both the written and the coding homework. And I think Catherine had prepared some stuff she wanted to present about what the applications of the stuff we're learning now are to computer graphics. So I have no idea what she's going to say, and I'm super excited to hear that stuff. So she would need to be here to do that, but I guess I can get started. We can just start with questions. There were a few of you, I think 5 of you were in my office hours yesterday. And I know the one question I really flubbed on that I couldn't answer was the 3rd written question, or problem 3 of the written questions. And I finally figured that out this morning. So I'm in a position to give better hints on that now. And I did it with twice, actually. I did it using notation from vector calculus and with differential forms. His hint is to use differential forms, and that's doable. I think it's actually easier if you just use more traditional vector calculus, which divergence and gradients and all that stuff. But if people want, we can talk about that, or Catherine wants, we can talk about something else. Catherine, I was just telling while you were gone that our plan for today was just you were going to talk about some graphics applications, and we were going to give them hints and whatnot for the homework. Do you want to, your mic's off, Catherine. Do you want to, yep, no worries. Do you want to start with
Sure. How's everybody, I mean, maybe we just went over this. How's everybody doing with the homework? And plus also, do people want more time to work on the homework? Okay. That's fine with me. I'm fine either way. Yeah.
Yeah, we were going to start new material today, and we pushed that back to Thursday anyway. So we pushed back what we're covering a day. We might as well give you all another couple of days.
Yeah, I feel like let's just have a laissez-faire attitude about the due date for this assignment, and I'm happy to give help at any time, maybe by the end of the week.
Yeah, sounds good.
Yeah. This animal really wants to participate in class today. So I was thinking about sort of like where we're at in the class and everything that we've seen so far. And I thought this might be a good time to talk a little bit about why people in computer graphics are interested in discrete differential geometry in particular. So I actually didn't make slides or anything. I kind of wanted this to be just like more of a chance for us to like stop and reflect on all the fun stuff that we've learned so far. Because what I think is really cool about the material in this class is that it starts to hit on really profound challenges, particularly in simulation in computer graphics. And, you know, even in just like 10 weeks, you know, undergraduates with really strong math backgrounds can understand things that have been helpful in graphics, like even just in the last like 10, 15 years. So I thought the example that I would use today would be cloth simulation. Have people heard before that like simulating cloth is one of those things that's really hard to do in computer graphics? Like if you go watch a movie that's like got a lot of special effects and then they have the little like featurette that goes with the movie that's like, oh my God, it's so hard to simulate water, or like it's so hard to simulate cloth. Like
Hair's another big one.
Hair's another big one. Yeah. So like cloth, well, okay. I would say the like big, so that area is called rendering, not of fat, but of images. So rendering just means like taking a abstract representation of like a scene in the world in a computer and like transforming that into a picture. So it's really just using a computer as a drawing machine. So figuring out how to like color in all the pixels of your image to make a thing. And you know, in rendering, there's been a number of like really difficult areas in graphics that have been challenges for like 30 years. So things like the transport of light around a scene. You can imagine like the world around you, like all of the photons that are like bouncing around, right? Like, you know, I have some natural light coming in a window. I have, you know, maybe some filtered light coming through like a curtain. And then I have light that's like intersecting with surfaces and bouncing back and all this kind of stuff. So that's one of these problems. You can kind of already just thinking about that as like little individual interactions happening between beams of light or photons in a scene, like that's incredibly computationally expensive. So figuring out ways to like move light around or fake moving light around in a scene is one of these big problems. But there's also more like physical problems, and that's where geometry comes in. So by physical, I mean like modeling objects or looking at, you know, if an object undergoes some deformation, right? Like some forces are acting on an object, how does that physical model change over time? And if you remove the force or change the force, how does that object kind of react and come to some equilibrium, right? So that's another like really difficult problem. And when we talk about things like, in particular, liquids, fluids like smoke or steam, these problems are kind of compounded and they interact with one another. So take, for example, like a foggy day, right? So fog, oh no, maybe let's use a different example. Okay, let's use like a fog machine. Have people seen that before? Like, I don't know, like a rock concert or something like that. And then they have like a machine and it like puts some gross smelling, I don't even know, this will be an internet rabbit hole for me later. But like, okay, so like there's some cloud that comes up out of it, right? And so you have to model, first of all, how do you model that object, right? Like it doesn't have a surface the way some of these things we've been talking about so far have, right? Like it's not like a thing that you could touch. So you have the problem of being able to like interact with that cloud of fog with other objects in the scene. But that fog itself is what we would call a participating media. So that means that light will interact with that fog. So if you have fog in between your light source and your camera, that fog might prevent you from being able to see through to the things on the other side, for example. So all of these different problems end up having to kind of like interlock, right? So we have the problem of modeling the surface itself. So where does the fog begin and end? how does it interact with the light around you? How does it interact with other objects? And so on and so forth. So, so liquids and fluids, like fog or air or smoke or things like that, that's another classic kind of area of things that are really challenging to approximate in a simulation or in a digital landscape. But another one is things that we would describe as being thin shells. So like a piece of paper. This is actually incredibly difficult to simulate. Even though you might look at it and be like, oh, well, I could just say this is a 2D surface, just like we've been doing. I want to triangulate this. I think I have a triangle. See, I'm already started, right? So, you know, I might say, all right, well, I want to like approximate this surface with a bunch of points. Those points, I'm going to say, okay, those are going to be the vertices. I'm going to draw edges in between them and so on and so forth. But then over time, you could kind of imagine in my simulation, well, how do I get this crease, for example? Like, how do I represent that in my simulation? If I want to say, for example, let gravity act on this surface, right? Like, if I want gravity to act on this surface, you could imagine that's actually a force is going sort of in the opposite direction as this curvature, very sharp line of curvature we've been talking about. So in some sense, the surface is relaxing. But that's going to depend on the medium, you know, the medium itself. How thick is the piece of paper? Is this a piece of paper that's kind of unstretchable? Or is this something, maybe this is, I don't know, like a rubber sheet or something like that, where it might have a little bit of give? How would that impact sort of the sort of position of the surface, like in response to external forces? And this, even though it like looks and behaves really differently than cloth, is actually the same problem that we have with cloth. So I don't know where this fabric came from, but I find it delightful. Okay, so does everybody know? All right, same idea, right? So we have a very thin material. We could imagine modeling it as just like a triangulated surface. Has anybody done weaving before? Matthew, have you done, you were talking about crochet, right? Can I unmute?
There, I am muted, sorry.
Have you done any weaving?
I've never done any weaving,
Has
unfortunately.
anybody done
I've
before?
seriously been crocheting, unfortunately.
Like what kind of weaving? I did the stuff where you make coasters when you're really little.
Yeah. So making fabric is actually the exact same process as that. So when you make fabric, you start out with which one's the weft and which one's the weave? Does anybody remember? Anyways, if you've seen a loom before, this one's the weft and this one's the weave.
The weft, the straight lines go all the way across, and then the weave goes in between them.
Okay, so you basically have a material where you start out with sort of like guide fibers, I guess, and then the cloth itself kind of goes in between the guide fibers. The weave goes in between the guide fibers like that, and you end up with a material that has sort of like basically principal directions. And the consequence of this for the material property is that if you take a piece of cloth and you look at it really close, like if any of you are wearing jeans, it's pretty easy to see. You'll have one direction in the direction of the weave where the material is actually quite stiff. And then at 90 degrees to that, it'll also be pretty stiff. But if you look at 45 degrees, it's really stretchy. Because if you can imagine sort of like a grid, if you pull this way, it's stiff. If you pull this way, it's stiff. But if you pull at 45 degrees, the fabric can go like that. And so you end up with a little bit more stretch in some directions versus others. And that direction is really important in sewing and in textiles generally. So that 45-degree angle is called the bias of the piece of fabric, okay? So keep that in mind. I'm gonna show you another piece of material. All right, does anybody here have a really fancy tie? This is a fancy tie. Has anybody ever been curious why ties are so expensive? Right, like you buy a tie, like you can buy a nice silk tie. They're like, look at how much fabric this is. Why is a nice tie like $50 or whatever, right? And it turns out that ties are cut on the bias. So if you were to take a piece of fabric like the one I just showed you and want to turn it into ties, the way that you do that is by cutting along the bias like this. So in order to get enough fabric to make a tie, you actually have to use like a huge piece of fabric because you're not able to, cut out the pieces of the tie in the direction of that like 90 degrees. And the reason why you do that, the reason why ties are cut that way is because when you have the direction of the bias in the direction of most of the forces, you get well, it could be a scarf or anything. You basically get an item which is going to lay flat. So if you have a tie that you can actually even see, if I hold this fabric in the direction of the weave, and you can kind of see, it's the stiffest direction like this, right? And so what that means is that when you look at the sort of like folds that form, see how it looks kind of boxy, kind of stiff? But if you allow gravity to pull in the direction of the bias, it lies much more flat. And that's because you're allowing the material to stretch in the direction that it's most stretchy, and it'll actually conform to the underlying surface much nicer. Usually that surface is like your nice suit or whatever, right? So that's why ties are cut on the bias. And the other garment that you'll see often cut on a bias is skirts and dresses. So if you ever look at like especially like a beautiful movie from like the 1950s with like flowing satin like evening gowns that like no one would ever wear anymore, those gowns are almost always fabric that's been cut on the bias. And the reason why that's done is because, particularly on a more like curvaceous figure, if you have the fabric cut in the direction of the bias, it's going to conform to the body in a much nicer way. You're not going to see the seams. It's going to lie flat. And the skirt or any part of it that's draped will drape really nicely, and it won't have these sort of like boxy folds that we see when we're sort of cutting our fabric on the direction of the weft and the weave. Okay, so basically that's all just to say that if we are thinking about these problems as computer scientists, right, or in particular people in computer graphics, it's really, really hard to come up with an encapsulation of a 2D surface that represents something as complex as a dress or a tie or some other like thin film or even something as simple as a sheet of paper, in which we can actually do things like encode, for example, that this piece of fabric is actually more deformable in this direction than in this direction, for example. And as we're thinking about like even things like our cotangent Laplace, right? We could imagine that tying in really nicely to something like this, right? Where we have we know where the curvature is the highest, we know that there's a force acting in a particular direction, but we want to be able to capture things like, hey, maybe this paper is going to be able to stretch more along some edges than on others. Okay, so I wanted to show you like a little piece of computer graphics trivia. Can I screen share, please, Dave? I promise it's legit. Oops. Okay. Okay, who recognizes this movie?
The Matrix?
Which one?
Second one, yeah.
Second one. Okay. So this movie is like 2002, 2003. So, you know, from our standards, I would say this movie would probably be, they were using quite advanced computer graphics for the time. So I would say this movie would probably be about like TV special effects of like 5 years ago kind of thing, right? All right, so this scene, if you talk to somebody in computer graphics, they will, and you say something about Gumby Neo, they will know that you're talking about this scene. Okay, so it's a very silly fight scene. It's a bit dark, but see if you can pay attention to the long coat. Okay. What did you see when you were looking at that coat? Do you want to see it again? Yeah, okay. That's a good shot right there.
So maybe I'm just seeing things, but it kind of looks like there's this path in space, and it's moving along that path where like certain parts of the cloak that were in one place move on, and then the other parts of the cloak move to the place where the previous part just was.
Mm-hmm. So maybe we're seeing some simulation artifacts. Did that coat look like cloth to you? I've just primed you by showing you a very stiff, like tablecloth fabric. But did that look like it could have been made out of this to you?
Yeah, it somehow didn't look like a real cloth. Like it looks like something else, but I can't really tell.
What do you think, Riley? What do you think they made that jacket out of?
I mean, isn't he in the Matrix in this scene? So it's just simulation anyway.
Yeah, so it's not a real, so the first question thing is it's not a real jacket.
It's not a real jacket. It's a simulated jacket.
I always look at that and think, wow, Neo's wearing like a full latex, like rubber sort of thing. That's why people refer to that as Gumby Neo, because not only is the model kind of Gumby, like the actual model of the human, the skeleton, like it kind of looks a little bit rubbery. I mean, they have a really good like face model on it. Like they're grafting on some like a nice like facial capture. But if you actually look at the body and the clothes, to me it looks like a rubber sheet. Okay, so you can contrast that with oops, I think we've had enough of that. You can contrast that with.
So Catherine, was that actual fighting that was done there? Do you know if that was all computer generated or was it just motion capture?
Oh, it's animated. Yeah.
The whole fight sequence is animated.
Yeah, it's all animated.
Yeah.
Yeah, I mean, so this is a sidebar, but the use of motion capture in special effects in particular is extremely contentious because I think that there's a narrative out there that performance capture is like this avant-garde acting, like the Andy Serkis sort of theatrical featurettes kind of stuff that people see. And the truth of the matter is that I don't know of any studio that does performance capture direct into like what you're seeing on screen. Even when most performance capture is actually used as a reference for animators. Because
I would have assumed like with motion capture, they usually like they put these spots in the body and then they just capture a skeleton of the object that's moving and then they animate over the skeleton.
they do, but they'll usually use the motion capture as a like almost like previs. So they'll use it to do like the starting basically like the first pass animation. But the rigs that you actually build to produce, particularly facial capture, so like facial animation, they don't the like. Do you know what I'm talking about when I say rig? So this is like so imagine like we're animating my face. So there's going to be certain like control points that maybe like, you know, I have like a squishy little bit of cartilage on the end of my nose. This might need to move in certain circumstances. You're going to have like all of the sort of like little muscles to actuate, you know, eyelashes. Around the lips is extremely difficult. That's an area that typically looks really bad in facial animation, just because the amount of expressiveness that you have in a real face is, it's very difficult to create kind of control points to like get all of those deformations. So when you're doing facial capture, they usually just totally ignore the mouth and just animate the mouth because the noise that you get in from the mocap rig is just like too great for the sensitivity that you need in that particular region of the face. But it's weird because I think people really like the notion that you could have a human performer, like, you know, you could hire Benedict Cumberbatch to come in and be a dragon, and that then you see him as a dragon, but really what you're seeing is an animator's interpretation of that performance, because animators are the ones that have the eye for that kind of detail. And in fact, particularly in character animation, what you see is that what looks convincing in an animated format is actually not necessarily physically accurate. And so you need to kind of like push the physics a little bit to make things actually look right in animations. And that is a matter of training and experience, how to do that. Yeah, that's like a separate project that I worked on when I was at Pixar, actually, which is really interesting. But that was in 2D animation, so it's a little bit different. Okay, so I'll show you one more Neo. Can you still see my screen? Yes? Okay, cool. All right, so this is the first Matrix. So this is probably like 1998. So this is like 5 years before. So I want you to look at the jacket in the same way. Oops, there you go. Okay, thumbs up, that jacket looked better. Thumbs down, that jacket looked worse. Okay, and that jacket was made out of?
Real cloth?
Actual cloth. Yeah, so the reason why this effect holds up so much better than the Gumby Neo was that they actually didn't do any computer animation at all in that shot. That shot was a completely practical effect. So they took like just normal DSLR cameras and they just built a rig to capture an actual jacket in the studio. And then it's all green screen, so you end up with, everything else around it is CG. But the thing that's the most difficult thing to simulate is real. And the reason why that one looks good is because if you think about, like, some tailor made that jacket for the costuming department, right? And when you make a jacket, like, yes, you have, cloth. It might be lined, which will give it some different properties in terms of like how it looks when it's sort of being deformed. You're not going to get a lot of stretch in the type of fabric they were probably using, but what you do get is sort of differential stiffness based on the location of the seams and the material and the thickness of the seams. And so that means that when he's like leaning back and you see these sort of like flapping effects, you can actually see that the material is reacting differently based on the position in space relative to the jacket itself. Does that make sense? So it's not like Matthew was saying, it doesn't just look like you're advecting a rubber sheet like over the same sort of like points in space where it's undergoing the same forces. It's actually like, if it's flapping a little bit, the amount of movement and the type of movement is going to be impacted based on whether or not, the point is here on the jacket or here on the jacket or here on the jacket, etc. So that's all a cautionary tale to say that, this is something that's incredibly easy to do badly in computer graphics. So a lot of people that were interested in this early on were looking at, for example, let me pull up. Okay, so this is one of my favorite papers from like early differential geometry. This is written by a guy named Eitan Greenspun, who's a professor at Columbia now. Okay, so this paper, so this is from Eurographics 2003. So this would have been maybe like within 3 or 4 years of like some of the first papers discussing like the D operator and the Laplace operator and like all of these different ways of like triangulating surfaces and then doing differential geometry on those discrete surfaces. And so the problem that they were looking at was exactly this thin shell problem that I was just talking about, sort of like how do you express different sort of like starting and ending configurations of surfaces that are really only triangle meshes. And so what they were looking at was, here, let me see. Okay, so we're gonna look at, I think, where are you, my little baby? I wanna show you a hat. It's a very important hat. This is a computer graphics hat. Okay. Oops. Okay. Well, all right. Well, there is a video. Can show you. I think you will not be surprised to know that this video is in such an old format, I can only show it to you on like an old-timey command line program. Turns out video codecs have changed in the last 15 years, but okay. Oh, there we go. Okay, super. Okay, so check out this straw hat. This is a video. Okay. Nope. I thought I was going to. Oh boy. All right, well, I give up. You can take my word for it that there is a video of a hat. So imagine in your mind's eye, you can simulate it, dropping the hat in here, a straw hat. You could imagine, for example, let's see here. Let's go back to the paper. Okay. There we go. Okay, we're back. This is the video I was trying to show you. Can you still see my screen? Yeah, okay, cool. Okay, so here's the problem. We want to be able to encode something as complex as the starting configuration of this hat, but we don't want to triangulate the volume. We don't want to have like tetrahedra and stuff like that. We want to be able to do it with just a single surface mesh. And so the way that they came up to do this basically does the following. So everybody remember writing that delightful dihedral angle function in your homework? Okay, so the dihedral angle, just to remind you, is if I have a triangle, something, you know, piecewise flat part of my surface, I have another triangle, piecewise flat part of my surface, I can basically look at it from the side and see how much bend there is between those two elements. And the angle in between them, that's called the dihedral angle. And so the big idea behind this paper is that if you have a thin shell, it could be a hat, it could be a piece of paper with a crease in it, at rest, you can think of like this region as having dihedral angles that are almost zero, right? Because it's pretty much flat. And at rest, this side, you know, all these triangles would have dihedral angles of zero. And if you triangulated this crease here, you could say, okay, well, at rest, the angle between this triangle and this triangle is whatever that angle is. And then if I put this thin shell into my simulation, I can apply forces to that surface and measure how much the surface has deformed from its rest configuration. So maybe I don't need that much external force to maybe this part of the paper bend a little bit. But if I want to flatten out all of these triangles, I'm going to have to take it quite far away from its rest configuration. So those dihedral angles will bend much more severely. And for each sort of like edge, so for each intersection, or sorry, each interface between two piecewise flat regions, so edges that connect triangles, you can basically say, how stiff is that edge? So imagine putting a spring across each pair of triangles, and then that'll basically allow you to control for every point along my surface, how easy is it to deform that edge away from its resting dihedral configuration. Okay, so for example, if I wanted to introduce a new crease, I might have to sort of bend a whole bunch of edges a lot. But if I wanted to, you know, flatten the whole thing, it might start out by flattening this edge if the crease was really, if the springs were really weak there. Does that make sense? Okay, so this paper does something that's really common in differential geometry, which is that it, I can find my, there we go. So basically what it does is it says, okay, well, what we want to do is we want to express that deformation as an energy. So we're going to say, okay, we're going to define a bending energy over my surface. And that bending energy is going to be expressed as the difference of mean curvature between the starting configuration of the surface and the deformed configuration of the surface. So that's what this expression is saying. So it's basically saying, okay, I want to look at the embedding of this surface in R3, and I want to see how much it's changed from my rest configuration, and I want to minimize that bending energy. So as I allow my hat to sort of like interact with the forces in my simulation, I'm going to always be trying to come up with a configuration of all of those triangles that minimizes this bending energy, because that's going to look natural. That's what's going to allow me to have something that looks like this, where it kind of preserves that starting feature crease, as opposed to just smooshing out like a piece of rubber, which is not what we want. Okay, so by doing that, what we can do is we can say, all right, well, I want to make, for example, a rubber beam, and that rubber beam might have, you know, some sort of like stiffness overall, and we can even do things like capture. If we start out with a rubber beam that's got a V in it versus like one that's kind of more noodly, you can see that it'll be stiffer in some directions than in other, and it allows us to create kind of more natural interactions between thin shells and physical forces. So for example, for some reason, I always found this particular figure to be really pleasing because it's so obvious, right? That if you have a piece of paper and it's like rumpled, and then you try to hang it from a wall and it's under the force of gravity, like the rumples don't go away, they stay there. And one way that you can kind of capture that initial configuration of the surface is by encoding these dihedral angles in the starting surface. And so this is something that's like, to me at least, like very obvious that we would want to be able to do this. And it allows us to do things like encode these thin films as sheets, as opposed to like triangulating a volume and doing something else more computationally intensive. So anyway, so pardon me. So if the people in the Matrix had used something like that for Gumby Neo's jacket, they would have been able to say, okay, well, this isn't just one sheet of rubber. They would have been able to say, okay, this is a thin film, but it's got these anisotropic bending properties where maybe it stretches more in one direction than in another. It might have an initial configuration, for example, that this lapel or collar or whatever is, you know, in a configuration like this, and then it's going to take a much bigger force to kind of like flip that up than it would if we were looking at, you know, some other part of the jacket. So anyway, so that's one way that we can sort of use our intuition about configurations of triangles, forces along particular areas of that triangulated surface, and come up with simulations that are more sort of like more readily approximate what we would see in the real world. And so if you look at things like, for example, this is a really classic way that computer graphics people like look at, in particular, fabrics. So this is a different bending model. So it's not using the squared distance between the dihedral angles or the curvature. It's actually using a slightly more advanced model that looks at quadratic forces of bending, but it's a very similar idea. So this is really typical in fabric papers in the graphics literature. What they'll do is they'll take a canonical kind of setup, like this one, like a square of cloth over a sphere you see all the time. And so what they're doing is they're basically taking that bending parameter that they're using, so like how much the sort of change in angle affects the final outcome. And all they're doing is tuning that spring. So they're saying, okay, well, in this case, it's not a linear spring, it's a quadratic spring, but it's the same idea, where, you know, just changing that one parameter allows you to capture the behavior of like a stiff piece of rubber, a like soft, silky, like piece of gauze or something like that. And you're using the exact same simulation. And that kind of expressivity in these types of models is really important to sort of being able to capture a wide range of behaviors.
Catherine, do you know if like the fabric simulations that do they have principal directions where they have one bending stiffness and other directions where they have a different bending stiffness?
Mm-hmm.
Really
Yeah, that's really common. And in those types of setups, what you want is actually to have a triangulation, which also sort of like agrees with the principal directions. It's also a reason why when we're doing things like Laplacian, applying the Laplacian to do things like anisotropic smoothing, it's really important to know like what the principal directions of curvature are, because if you have like an edge in a triangulation, and it's possible to see that the difference between the maximum and the minimum direction of curvature along that edge is really high, that's a really good sign that that edge is actually on a boundary or on a crease or on some sort of like global position along your shape upon which we might actually want to preserve that difference in curvature. So a lot of these smoothing methods actually look at encode the principal directions of curvature as a way of being able to see how the surface should deform. So I think one of the famous papers, I think I have it in here somewhere. One of the famous papers on this was the Mark Myers like ND differential operators paper from, this is like one of the ones where they like describe the cotan Laplace and stuff like that really early on. And they talk about that. Oh yeah, here it is. Okay, so so here what they're doing is they're applying the Laplacian operator to smooth a noisy cube. Okay, so does everybody see that? So basically all they did was apply Gaussian noise to the surface of this cube, right? And then they're saying, all right, well, I want to look at all these bumpy parts and I want to smooth out the bumpy parts to try to recreate an underlying smooth surface. So this would be simulating something like noise under scanning, for example. And like everything's, you could kind of imagine like everything's fine, I'm smoothing along here. And then I get to this cusp, like I get to this curve, and you could totally imagine over smoothing and basically turning your nice cube into a ball, which is in this case like not what we would want. But if we're actually able to look at the principal directions of curvature along the surface, we could see, okay, well, here the curvature is basically the same in every direction that you look. But if you go along an edge or even on one of these corners, what you'll see is that the curvature is changing really fast. And so by using this like what they call anisotropic smoothing, so smoothing that actually preserves these principal directions, you can preserve these sharp creases. So being aware of directions of principal curvature, it's a little bit, I don't know, I find this to be a little bit curious and surprising that a notion of curvature can actually help you preserve discontinuities in curvature, right? But having these sort of like globally mindful operators can actually help you do things locally that preserve global intrinsic properties of the shape. So that's I think that's kind of cool. Yeah, I think that's all I wanted to say about this. But maybe the like exciting message of this is that something like this thin shell model that I was showing you, you have everything in your toolbox that you need to be able to simulate a surface like this. Because really what you're doing is, you know, you need some time stepping to apply a deformation to a surface. The one that you'll use in your assignment this week is the implicit Euler method. They use Newmark time stepping, which is a slightly different, more stable method, but we have computational power now that we can actually take really small time steps and use less sophisticated numerical integration. But really what you're doing is you're defining a flexural energy in which all you need to know is the change in angles from the rest configuration and the local deformation from the rest configuration. And that's really all you need. And you end up building, like we'll see in this assignment, you end up basically building a big linear equation and then solving for the new positions of the surface using that model. So it's and this type of setup is really, really common in graphics. I'm hoping that at some point, maybe later on in the semester, I'll be able to show you a different project that I worked on that uses like almost the exact same methodology, which is coming up with an energy functional, discretizing that energy functional, figuring out a way to turn it into a big linear system, and then solving for the new positions of the points. And that's like, there's tons and tons and tons of really cool results in really different areas of computer graphics that use the exact same setup, and it's all enabled by having like well kind of thought out discretizations at the very beginning of the formulation of the problem. So yeah, I don't know, I think that's all I wanted to say about that. I just want to make sure that you knew that all of this like surface encoding kind of stuff that we've been talking about is actually stuff that like really helps, like doing it right really helps solve some of the most difficult, pernicious challenges in graphics. And it does it in really elegant ways, like this thin shelf thing. So yeah. I'm happy to answer all of your questions. I'm happy to like show you more pieces of fabric I found in my house.
One more cats.
Cats, well, okay, there is a bug in here and she has been hunting. She's staring at me like a wild animal right now. So we're living in an incredible age.
Does anybody have any questions about anything Catherine said? I have zillions of questions, but I could ask you another time.
Blacked out and talked about fabric. I'm sorry. This is all that happened.
Very cool. I love it.
But yeah, I think that, you know, when we were talking about like Kaylee and Julie and I were talking about this Cotan Laplace yesterday, and I just had this feeling of like, oh, it's shocking and bizarre that if you think hard enough, there's so many problems that on the face of it seem nothing like, you know, it doesn't seem like it's going to end up being like a linear system of equations or whatever. And then if you come up with like the right energy functional for something or whatever, and you know, you can come up with an expression where you have like you know, a positive definite matrix on one side, then it's like you're off to the races. And so I think it's a really fun area that shows a lot of, it connects like your visual intuition as like a human being interacting with the world. Like I think we can all look at Gumby Neo and be like, that jacket is whack, and like you know, and then but it's also like fundamental reasons of like geometry and like you know, just curvature and like all these other things that like make it difficult. But then there's really practical things that you can do, like figuring out how to approximate things well in a discrete fashion that allow you to actually get traction on the problem. So it's like really different brain areas, I think, personally.
Yeah, very cool.
So if we're graduating in a couple weeks and are going to be stuck at home with nothing to do and want to keep learning about graphics, what resources and software would you recommend?
I would personally recommend actually starting, I find for myself, like, there's a lot of things in computer graphics where the way that people do things seems really arbitrary. like the reason, for example, like I can give you, this is a very dumb example, but artists love working with what they call quad meshes. So basically like meshes, like a approximation of a surface that uses quadrilaterals instead of triangles. And everybody that does anything in geometry is like, triangles forever, like why would you ever use quads? Like when you use quads, you get like, you know, it's not necessarily piecewise, or it's usually not piecewise planar and all that stuff. Like there's all sorts of weird stuff like that, or like, you know, the way that we do, you know, most like scanline rasterization algorithms, like the order of operations there go back to like when people were using the VGA spec that had like certain line scan properties. And the reason why the VGA spec was that way was because people were using like CRT monitors. And it's like there's all this stuff that like the technology and the techniques have kind of co-evolved over time, that if you just like look at what people are doing right now, I feel that actually it can be kind of, it just feels all over the map. So for me, like I actually think it's much more interesting to look at graphics from like a historical perspective as you're learning about it from the beginning. So like reading, there's a great book, which I will remember the title. Jack is gonna remember. Jack, do you remember the name of that Pixar book that is, I feel like I recommended to you to read this book at some point. Is it the Pixar Story?
Pixar Touch.
Pixar Touch. There's a couple of books that actually talk about like the history of computer graphics, and they go through like, you know, oh yeah, that's the one. Good job, Jack. That is the one I was thinking of. Jack gets a gold star. Because there's a bunch of stuff when you actually look at like the history of graphics, like, oh, frame buffers used to cost like $80,000 a piece. And so we had like, you know, like all of these families of methods designed on like figuring out how to like maximize like, you know, weird stuff from like Atari days or whatever. And the ingenuity that people, particularly I think in like the like mid 80s to early 90s, that what people were doing with the technology that they had is really incredible, and I think gives you a lot of insight into like why some things are the way that they are right now. So I would definitely recommend looking at some more like overview kind of techniques, because I think that they can help prepare you for like why does Photoshop look the way it does right now? I mean, honestly, like there's stuff like that where it's just, when you plop into the tools that people are actually using right now, it's very perplexing. So yeah, that's what I would say, is because it'll give you a sense of like what the, like why when I talk about computer graphics, it encompasses everything from like, you know, rendering, we were just talking about geometry, you know, obviously we've talked a lot about, but also there's a lot of stuff in the computer graphics literature that's really about perception. There's a lot of stuff that's really about, you know, human factors and design. There's a lot of stuff in computer graphics that gets into issues of like accessibility. You know, there's stuff that gets into issues of power, you know, energy efficiency, and you know, the human visual system. That's what my research ended up moving into, which is weird thinking that I started with this stuff, right? But there's just like people that are kind of interested in all these different areas, and I think probably in another 50 years, computer graphics will have splintered into like even more kind of areas. But you know, there's stuff like even you know, if you're interested in, for example, like programming languages, right? There's stuff in graphics, like a lot of the early domain-specific languages were all for rendering. You know, there's a lot of stuff, a lot of work that had to do with the graphics pipeline, like the hardware itself, like that, the reason why we have general purpose programming on GPUs right now is because there had been all this research done, like literally in the 90s, so that teenage boys could like shoot zombies in like computer games. And then a bunch of people looked at this hardware and were like, what if instead of making bloodstains, we like solved big systems of linear equations? And then it was like all of a sudden like GPU like happened, you know, and like now, you know, when people talk about parallel computation, that entire field of computer science actually comes out of computer graphics. Like nobody set out to build hardware that was going to do that. Like people set out to build hardware that would allow them to play like zombie games or whatever, you know what I mean? So like I think some of that is really informative, and it's also just fun to look at I think the history of special effects and animation, because both of those are areas where like I think it's a lesson about humanity that when people first have a tool and that tool doesn't work very well, it requires just an incredible amount of craft and artistic sensibility to like make something with a rudimentary tool. So you look at early movies that used CG, like, you know, the Jurassic Parks and the, you know, the what am I thinking of? Little Mermaid and stuff like that, that were using these early computer graphics systems. And the people that were using that technology were really intimately familiar with the limitations of that technology. And that's why, you know, a movie like The Matrix from 1998 holds up so much better than The Matrix from 2003, because they were really aware that like, if they tried to simulate that cloth, it was going to look like trash. And so they used a photographic technique to do that. Whereas, you know, whatever, 3-4 years after Jurassic Park, we get like Jumanji, right? Has anybody ever seen Jumanji recently? That movie's horrifying. Like if you see that now, like you can watch Jurassic Park and like really enjoy it, because they're using animatronics for the things that computer graphics couldn't do well, right? And so with a lot of these technologies, it's like people do it once and then everybody's like, nailed it. we solved animals. Let's do Jumanji now. And then they make something that's going to give you nightmares for like generations. Do you know what I mean? And so I think that like that is like a thing that we see over and over again with like machine learning and with, you know, all sorts of predictive modeling and, you know, like modern data science. Like a lot of what's going on there right now is like all of these ethical considerations of like, look, we can do a thing. And it's like, but should we do a thing? You know, and with graphics, it's just like in your face, like, you know what, we should not try to simulate the ocean in this way or whatever. Like, you know, use a water tank and then matte paint that shit in there and it'll look great for forever. So I think some of that stuff is really fun too, because it allows you to kind of look back and really appreciate when people have done really well with technology that was super rudimentary. Yeah, and like, I mean, Toy Story is the same way. I mean, if you go back and watch beginning Toy Story, like they did toys for a reason, which is that simulating plastic surfaces is something that they could do in a computationally efficient way. And the fact that that movie even got made is remarkable. Like you talk to the people at Pixar that worked on that movie, and like literally they animated by changing joint angles in a text file. Like it wasn't like they had some like visualization of like, I'm gonna move Woody like this. It was literally like having an idea in your mind of like where you wanted his arm to go and like changing a bunch of values in a text file and then prevising going and having a coffee and coming back and like seeing this, you know? And so it's just like the staying power that you have to like be able to use tools that are really limited is shocking. So that's what I would say. look back at some of the older, there's been some really great books on the technology. And I think, watch some old movies, and it'll give you a sense for the areas that you find interesting. And then you can kind of look into more about like how they do particular things.
Should we move on? We don't have much time left. Should we move on to homework questions?
Yes, definitely.
I have a bunch of questions.
Bunch of questions.
I don't know if they're best saved for office hours or anything. One of the things you mentioned is that 6.3 is possible.
It is
I
possible.
thought that was the hardest question of the bunch.
Yeah. You want a hint? I can give you hints. I thought very hard on how to give you all hints for this one. I'll share my screen. Catherine, you want to stop sharing your screen?
Oh, yeah, how do I?
Maybe I could just stop you. There we go.
I did it, I think.
At some point, I will share my screen. Notice it takes some time.
You got to take your time. You got to do it one step at a time.
Yeah, the whole share iPad screen thing, it always takes me like 3 tries to get it right.
You should ask Kaylee how much time she's wasted with me trying to figure out how to get my tablet set up so that I can draw on it. Sometimes I have to use all of my bad words.
It's entertaining. It's entertainment value.
Oh, hey.
Ooh.
Oh, and now it disappeared again, didn't it?
No, we can still see it. Or at least
Oh,
I want to play math games. Wait a minute.
math. Oh, yeah, those are fun.
Oh,
There's
I needed it.
There's the earth in hyperbolic geometry. No, that's Euclidean geometry. Let's see. Space.
Yeah. Ooh.
Yeah, there's all kinds of cool stuff going on here. There's a whole lot of differential geometry happening here.
Does your iPad get hot when you're doing this?
No. It's in fact, this app is super old. Like it ran on the first iPad.
Oh. Good job, whoever did that.
Yeah, it's Jeff Weeks. Really amazing guy. Let's see. All right. Let's see. What was I doing? Oh, I was doing this. Right. Oh, don't look at that. That's the answer. Don't look.
Eyes closed. Eyes closed.
All right. It's blank.
This lecture's recorded, right?
Yeah. All right. So here's what you have to do. Let's see. You've got to prove that. Oh, sorry. Let's back up. So the problem is you've got this inner product between the Laplacian of f and some function g. And you want to show that equals the negative of the inner product of the gradient of f and the gradient of g plus the inner product of the gradient of f dotted with a normal vector with g, but that is taken over the boundary. So, all right, step number 1 is understand what the hell the question is and what all this notation is. And then I'll give you a hint because I'll unpack the very last term because I think the very last term is the key to all this. And he has a hint in his notes that you should do this with differential forms, which is doable. I went and did it that way, but I do think it's easier the vector calculus way. So I'm going to show you, I'm going to give you a hint the vector calculus way. All right, so first, if you read his notes, he's got 2 different definitions of these bars. So if you've got 2 functions, the bars mean just integrate the product of those functions over some domain. And this is really, if you read the problem, I think the context is that this domain is just a region of the plane. So this is some 2-dimensional domain in the plane. So this is really the integral of a function over the plane, dA, or you could even write that dx dy. So it's just a double integral dx dy of some function. So again, omega is just some region here, omega. The other thing to understand is that there's a different definition if you have vector fields, V and W. V and W are vector fields. Then the thing you're integrating is, again, their product, but the way you get a function to integrate is by taking their dot product. And that gives you a function to integrate over omega, right? So that actually, this, let's see if I get some colors here. This is what's going on here. Here we've got two functions. The Laplacian of f is a function and g is a function. Whereas this is two vector fields. So you have to use this definition. And so that's representing a dot product. And then there's one more thing to understand, that this boundary operator on the bottom, that means we're integrating over the boundary of omega. Okay, and again, those are two functions, but n there is the outward pointing normal at the boundary. So we're just integrating over the boundary of omega, and we're integrating the gradient of f dot n. So grad f is a vector, n is a vector. So grad f dot n is just a function again. We're just taking the dot product. So this is another function. So here we just have, so that function times g integrated over the boundary is what we're doing, okay? So I think it's clear to rewrite the original statement, this whole thing. You can rewrite it just by unpacking the definitions he's got there. I'm just gonna rewrite it. This is the integral on the left side here. Those on the left side, you've got that inner product. He's just talking about the integral over omega of the Laplacian of f times this function g, okay? And there's a dA in there or something, or dx, dy, however you want to do it. And you want to show that that equals the integral over omega of the gradient of f dotted with the gradient of g. There's a negative sign there, plus the integral over the boundary of omega of the gradient of f dotted with n, all that times this function g. And that's an integral over a curve, so there should be like there really should be I'm going to be a little sloppy about this. I'll write it in right now. There's really a dA here, which is this just shorthand for dx dy. There's a dA here, but there's a ds here. It's just, if you think about the arc length parameterization of that curve, we're integrating with respect to arc length going around that curve. It's just, when we think about it in vector calculus terminology, that's a line integral as opposed to just a two-dimensional area integral around the boundary there. All right, so here's I'm not going to finish the problem for you, but I'm going to give you lots of hints by just attacking that last term. I am going to unpack that last term for you, and then the rest will be easy, okay? So this last term, first of all, let's think about that g. So I've got a vector field dotted with n times some function g. So I've got a vector field, a vector, so at every single point there's some vector I'm going to dot with n, and then I'm going to multiply by some scalar, which is the value of g at that point. So one thing to recognize is that I can multiply the vector by the scalar first and then dot it with n. So you can move that g inside and make this the integral over boundary of omega of the gradient of f times g, that term. Oops, what did I do? That's an equal something. Dotted with n. Everybody see what I did there? All I did was just move the g inside the dot product, right? If I take a vector, if I dot two vectors and then multiply the result by a scalar, then I could take that scalar and multiply it by either of the two vectors. I could have also moved that g over to the n side. Another way to say that, so a fancy way to say that is that the dot product is bilinear. So if I multiply a dot product by a scalar, I can bring that scalar inside the dot product into either of the two vectors. There's lots of ways to say this. Okay. All right, now that term there. Whenever I see an integral of anything around a boundary, I always think about Stokes' theorem. This should be an integral of somehow the derivative of that inner stuff around just omega dA. And what goes in the middle here should somehow be the derivative of this stuff. If I differentiate that stuff, and think about going backwards, Stokes' theorem says that you could undo the derivative at the sacrifice of passing over to the boundary, right? But you got to think about what is derivative in vector calculus. This is exactly the name of this problem. He says prove Green's identity. This is what you learned in Calc 3 that was called Green's theorem. So Green's theorem, let me just remind you what Green's theorem says. Green's theorem says exactly, again, just crack open your old vector calculus books. And it says that the divergence of any vector field, the integral of that, dA, equals v dot n over the boundary df. And this is really a double integral. And this is an integral around a closed curve. So sometimes they decorate it like that in vector calculus books, but those extra decorations are not as necessary as understanding. This is just one instance of the generalized Stokes theorem. It's that divergence is what's acting as the appropriate derivative that allows you to change the integral from an integral over the boundary to an integral over the whole domain. Right? So again, like this is like straight out of your vector calculus books. Okay, so this is the answer right here. The question is, what's the appropriate derivative that lets us rewrite an integral over the boundary to an integral over the domain? And the answer is take the divergence, right? So if I apply that up here, what I'm seeing is the divergence of G times the gradient of F. Right, that's just Green's theorem straight out of your old vector calculus books. Okay, so what you have to prove is that this integral is equal to this integral plus this integral, right? Take the negative thing and bring it to the other side. Everybody understand what I mean by that? We want to prove that the term all the way on the right is the sum of the other two terms. Just take the negative thing and bring it over. Right? And now these are all integrals over omega. So I'm gonna rewrite what's left to prove. So we've rewritten this as a different expression, right? Now this is this thing. So what's left to prove over all this? All the way on the right is the integral over omega of the divergence of G times the gradient of F. And we're saying that is somehow equal to, here's what you have to prove. We got that very first term, which was the Laplacian of F times G over omega, plus the next term, which was the gradient of F dotted with the gradient of G over omega. Okay, so just by changing that last term, I'm using some basic vector calculus, I just replaced this problem with a different problem. And the way you prove that is to think about what happens when you take away all the integral signs. This is true if I take away all the integral signs, and then once you prove that, then you just integrate every term and it's still true. Right, so the point is, this is true because you're gonna prove that this is true. Oops, no. You're going to prove that this is true. right? This is what you want to show. Once you show that, then you just integrate every term to get that, right? And then you just work backwards here, go the other way to get the original expression. Right? I'll give you one more tiny hint. It's not such a tiny hint. You may wonder when you're working on the right side here, how is the Laplacian ever going to show up? And it's almost there because don't forget that the Laplacian of f is the divergence of the gradient of f. And that's almost here already on the right side. We have the divergence of the gradient. There's just that pesky g in the way, right? So you have to figure out how to pull that g out. When you pull that g out, you're going to pick up this extra term. Right, so you've got to think a little bit again about the definitions. Don't forget basic vector calculus, that the gradient of f is just, we're just in 2 dimensions here. So that's just the partial of f with respect to x, comma, partial of f with respect to y. That's the gradient. And don't forget that the divergence of a vector field is the partial of the x component of that vector field with respect to x plus the partial of the y component with respect to y. Right, so this is really all you need to prove this equality. So just unpack everything in coordinates and you could just prove that equality, and then integrate everything to get this equality, and then do the opposite of what I did on the very right side to get back to the original statement in integral form, and then replace that working backwards with the original problem in norm form. Did I lose everybody?
Oh, that was really cool.
Yeah, that was helpful. Okay.
Yeah, that's super helpful.
Yeah. It's that last term using Stokes theorem. And he gives a hint. His hint clearly he wants you to do it with differential forms, but the hint is the same thing. The hint is to use Stokes theorem somehow using differential forms. And that's really, it really amounts to the exact same thing. As that hint is really, it's the key is the very, very last term to somehow use Stokes theorem on that very, very last term and change the problem. This, by the way, people in my office hours pointed out, I asked them, hey, what does this remind you of the original statement? It should remind you of integration by parts, right? The integral of v du equals uv minus the integral of u dv. It's the exact same theorem. We just bumped everything up a dimension and used vectors and gradients and dot divergences as our derivatives and our functions. It really is the exact same theorem. Oh, 9 minutes overtime, crap. Well, since I'm here anyway, are there any other pressing homework problems?
Yes, I've got a couple. Is it office hours time? Should we do them now? Should we do them later?
Catherine, you want to just shift over to your office hours? You're muted.
I have another meeting that I have to take at 2:45 until 3:30, but then I'm available at 3:30. If it's a math question, you should grab Prof. Bachman now.
There's also office hours tomorrow, right?
Yeah, I have office hours tomorrow morning too. Yeah. Yep.
Are we saying both assignments are due at the end of the week?
Why don't we say next Tuesday? How about that?
Oh, lovely. That's very nice. Then it doesn't really overlap with clinic as much.
Very kind of you.
Yeah, I forgot about the clinic, all the clinic deadlines this week. So
Yeah.
I have a question for Prof. Breeden as well. So for the coding assignment, there's this recurring theme that I keep seeing popping up, the mass matrix, and it's used to like, in some way to transform from some continuous Poisson problem into a discrete one. I don't understand the principles involved in that, and as a result, I'm pretty sure that's what's breaking all of my code.
Okay.
We use the mass matrix. What is that for?
We can definitely talk about that in office hours, but I don't know that I have like a one sentence.
I could say it in roughly
You
one.
got it?
Yeah. I mean, the Laplacian, if you look at the course notes or the lecture I gave in class, the discrete Laplacian is this formula. It was evaluated at a particular vertex, and at that vertex, it was 1 over the area of the dual cell, the dual 2 cell, times the sum that involved these cotangents. And then this other term, fi minus fj, it's the integral over j, whatever. If you bring this to the other side, then you get the area of ci times fi equals this big summation, okay? This is the mass, where the mass matrix goes. The mass matrix is it's just a diagonal matrix where each entry on the diagonal is the area of the dual 2 cell corresponding to that vertex. So if you think of this as a matrix calculation now, if we're computing this simultaneously at every vertex, then what we'll have is this big matrix here with C1, C2, C3, and you're multiplying that by F1, F2, F3, etc. And then in each row, you get exactly this product when you multiply those two matrices. So this is what he keeps talking about as the mass matrix.
So would the general principle be, whenever you have a continuous Laplace operator, to discretize it, you grab the discrete Laplace operator and then multiply it on the left by the inverse of the mass matrix?
Yeah, well, I think this is really the discretization of the Laplace operator. It's
Okay.
just that to do it in practice, he makes a comment that you want to set it up as a linear algebra problem, and that linear algebra problem is more amenable to numerical techniques if you bring the CIs to the other side. So bringing the CIs to the other side isn't part of the discretization. That's more for computation purposes.
Oh, okay. Wait, so the thing you circled isn't the discretization of the Laplace operator.
It is. The thing I circled is the discretization of the Laplace operator. But the reason you bring it to the other side is not because of discretization. It's because you want to solve it in practice.
Okay.
He makes a comment. Now we're really getting to things I don't know much about, but he makes a comment that this term is represented by a symmetric matrix. When you multiply it by that 1 over ci, it's no longer a symmetric matrix, which means numerically it's much harder to deal with. So you bring those CIs to the other side, because now you've got this Cholesky factorization. I don't know what those words mean, but somehow that all works.
Yeah, basically we all know that diagonal matrices are also good, right? It's easy to invert them, so that's nice, which is what we're gonna have to do setting up this big system of linear equations. It preserves the symmetry of the cotan Laplace, which is good because the symmetry helps the numerical solvers that we're gonna use. But you have to remember that mass matrix is basically the Hodge star. Like you can think of it as a way to take the values of your scalar field, the scalar field upon which you are applying your Laplace operator, taking it from a discrete 0 form to a dual discrete 2 form. Yeah.
Yeah, this is another way. That's nice, Catherine. This is another way to say it, is that you can rewrite equation like this, and this is essentially when you take the Hodge star, that's the multiplication by the mass matrix. Mm-hmm. So it's really discretizing this equation instead of this equation.
The inverse mass matrix. So it'll be the areas, not 1 over the areas. Yeah.
It's the inverse mass matrix, right?
Other question, what is rho bar? I saw that one pop up and I have no idea what it is.
Yeah, so he makes a comment that the Laplacian of any function rho is the same as the Laplacian of rho plus or minus any constant. And the reason why you want to subtract that constant is it somehow recenters this distribution. I don't really understand this terribly well. I understand why adding or subtracting a constant doesn't change the value of the Laplacian. I don't know why this particular constant is the one you want, but this is the hint I was going to give people. That rho bar, apparently the right one is 1 over the area, the total area of the surface, times the integral of rho over the surface.
That's not even killing it.
I don't know why that's the right thing to subtract. I didn't figure that out until I looked at the solutions.
Okay. Wait, hold on. So how do we get the area of the surface?
It's one of the helper functions you already built in the geometry code.
Oh, just like gets area of like a mesh or something?
Are you
Yeah.
kidding?
Yeah.
Okay. Cool.
Yeah, it's total area of the mesh. Right.
Integral.
So this is the
Yeah, I think
continuous formulation.
the idea is that you want to remove any constant component on the right-hand side of that linear equation.
You liked
But
created by.
Hey Jack, you should mute yourself. But I think that
Sorry.
no worries. But I think that it's mentioned in the course notes on page 101, but it's not super explained well, and I can definitely get like a better explanation of that. But the skinny on it is that by removing that constant factor, you're able to employ numerical methods to find the new value of u.
Okay. Cool. I think that mostly wraps up that for me, I think. I have some other questions, but I can come in for office hours later. Thank you.
Cool.
All right, we'll look forward to seeing you in office hours, everybody.
All right, bye everybody.
Okay.
Thank you.
Bye.